Um, um, so today I'm going to be doing the bold thing of trying to talk about large language models at a statistics seminar. But hopefully by the end I'll sort of convince you that it is reasonable underlying stats going on here, and that it's really going to be an application of kind of solid statistical decision theory in this sort of large model setting. So what we're going to be looking at is basically trying to gather information in these large language models. In particular, trying to get them to sort of ask questions of users and kind of interact with them in a kind of sort of more agentic way, rather than just being sort of purely responsive. And the basis we're going to do that with is the idea of Bayesian experimental design, and in particular, information theoretic approaches to Bayesian experimental design. So to give some motivation, consider trying to do the problem of 20 questions with a large language model. So the way this works is that we say we're sort of thinking of something, in this case, a famous historical person, and then some kind of answer needs to, someone needs to then ask us yes or no questions to try and figure out that thing we're thinking of. So here they're going to ask yes or no questions to figure out that person. And we're going to try and play this, in this case, with GPT-4, using the prompt shown on the screen. And the first question it tries to ask us is the person you're thinking of male? And we say no. It then asks, is the person from the 20th century? We say no. So far, these maybe aren't perfect questions, but they're certainly very reasonable questions to try and figure out a person. But if we sort of skip through to the 11th iteration, we see that things have really started to go quite awry. So it then at the 11th question says, did this person live in the 17th century? No. Did this person live in the 18th century? No. So it's got itself here in a bit of a loop of just kind of asking century by century. And then it goes even worse. It sort of says, this means the person you're thinking of lived between the 15th and 19th century. Did they live in the 20th century? And obviously, this has now got to a point of quite ridiculousness in the questions it's asking. And in fact, even then, when we say no to this, it then absolutely decides this person must have lived in the 20th century. And so you see that the system has got really quite stuck. So this is an LLM that's about a year old. They have got a little bit better since then. It's not quite as sort of catastrophically funny in how it fails anymore. But the idea is still there, that these large language models are really not good at kind of seeking out information or asking questions, particularly in this kind of sequential setting. So the sort of premise of the talk is going to be trying to look at how we can kind of improve this. So how can we make these large language models much more proactive, and how can we use them to make decisions and seek out information by asking questions rather than just kind of giving us answers. What I'm then going to present is this approach called BED-LLM or BED-LLM, and this is going to basically combine these large language models with the idea of sequential Bayesian experimental design, which is a much more sort of formal statistical framework for gathering data and running experiments. And what we're going to find is that this gives us much better ways of asking questions and gathering information in these LLMs, but it is going to require quite a few kind of nuances in how we set things up. We're going to see that working in this LLM environment takes us kind of quite outside our comfort zone of sort of normal Bayesian models, and there's lots of things we then end up having to kind of do to kind of make things work. Just to sort of whet your appetite a bit with this, these really is going to work. It's not something we're talking about here where this is going to kind of be little marginal improvements. We are going to be able to take some of these large language models and really transform them from things that kind of can't do something like this 20 questions class, as shown by the sort of green line at the bottom, up to things that really sort of can do this task when we introduce this sort of more formal Bayesian sequential decision making with this BED-LLM approach. It's also hopefully clear that kind of if we can do this, there's going to be a lot of kind of potential applications for this. Everything here sort of from trying to clarify what a user actually wants when they request it from the LLM, to sort of more interactive kind of multi-turn conversations. So if you could think about doing things like automating political surveys or market research, but also doing things like recommendation, tutoring, AI scientists, code generation, medical diagnosis. A lot of the things we actually want to sort of potentially use LLMs for in the modern world really require us to have this kind of interactive, proactive kind of behavior to them. And I would argue it's one of, if not the biggest way they kind of fall short at the moment. Okay, so with the sort of all that motivation out of the way, let's start looking things a bit more concretely and sort of formulate this problem and then show how we're going to do it. So we're going to assume that there's some kind of variable that we're trying to learn about, and we're going to call that theta. So what this is going to vary between problems, but it can be saying that 20 questions, it was the sort of person that we were thinking about. It could be some code that we want generated. It could be some predictions we'd like to make about something. It could be some ground truth about the real world. It's kind of anything we want it to be. But the key is that we need a concrete notion of something to learn about, because if we don't have a concrete notion of what we need to learn about, we're not going to be able to make concrete notions of what are good questions, and therefore we're not going to be able to sort of learn. The assumption, though, then is that we can refine any beliefs that we have in this variable theta by making some kind of queries. We'll call those x, and we're going to receive some responses y. So most simply, this is just going to be questions that are asked to the user, and that's going to be x, and the responses that the user gives are going to be y. But it could also be other things as well. It could be kind of sort of web searches that are done. It could be going and finding particular papers to analyze. If you're putting sort of an LLM in the real world, it could be actually going and running a physical experiment or taking real action. So it's anything where the LLM basically is making a decision, and then it's getting some information back through some kind of data. We're also going to assume that we're in a kind of sequential setting here. So rather than just having a singular query, we're going to assume that there's multiple queries x1 for xt. And we're going to assume that we're going to basically try to be adaptive. Each time we get some more responses, we're going to try and use those to inform the next question. So each xt here is going to be based on what I'll call the history ht, and ht is just the set of query and response pairs that we've already received. What we can then do is we can also use the LLM here to sort of go and try and derive sort of belief distributions things. So the LLM we can think of about as being some sort of really general model. And when we sort of feed things into that model, it is going to generate some distributions for us. So if we, for example, take that history, we can put that history in the context of the LLM, just sort of in its the history of prompts and responses it's had. And then we can just ask the LLM, for example, to sample what it believes theta might be. And that will induce some kind of distribution. And I'm going to be using the sort of the notation BED-LLM for this distribution. I could also sort of ask it to reason about responses, and then I would get a response on the BED-LLM given now say theta and xt plus 1 in the context instead. So there's a bit of sort of hidden prompting and things that are going in there, but the general idea is that we've kind of appropriately setting the LLM up. It's going to be able to sort of induce a distribution over anything we ask, and we're going to be utilizing those distributions in our experimental design framework. So now we've got the sort of the problem setup laid out. I'm now just going to sort of briefly go through the idea of Bayesian experimental design itself and how we can use that to sort of essentially design good experiments, which in this LLM context is going to be how we choose good queries, how we choose good questions to kind of be as informative as possible. And for this, we're going to be taking a sort of information theoretic approach, where essentially what we're going to try and target is what's called the information gain in these kind of target variables theta. So information is basically measured in reduction in uncertainty. So when we convey information, it means that we reduce our uncertainty about something. And so what we're going to have is basically that the gain in information we have from gathering some new data is going to be the entropy over what we're targeting, specifically the Shannon entropy over what we're targeting before, minus the Shannon entropy after we've gathered that data. So we have this sort of h theta minus h theta given data. And essentially, that's going to tell us that sort of good data is stuff that really strongly sort of reduces our uncertainty in our beliefs. So if we have something that makes us much more confident, that's usually going to be good data in terms of reducing our uncertainty. This then is obviously a function of the data, but that data is going to be a function of any design decisions we make. So whenever we run an experiment to get some new data, then it's going to sort of influence the amount of information we gain because it's going to influence that particular data. And so we can think about the experimental design problem itself as something whereby we're sort of choosing designs to try and maximize this notion of information gain so that we can kind of most reduce our uncertainty about what we're trying to learn about. So here you can got sort of two simple examples where we might have a sort of a small information gain if our prior essentially on theta to our posterior doesn't change much, but on the right we have a larger one where we've got a bigger reduction in a posterior. I'm just going to quickly see if I can get this thing to come off the bottom of the screen to hopefully make things a bit easier to see. Is the screen still showing okay for everyone?
No.
Ah, okay. I probably shouldn't have even bothered trying. What I'll do is I'll share the entire screen. That should then.
So Tom, at least for us, there was nothing else on the screen, so it might have just been on yours.
Ah, okay. So it was never a problem. Oh.
But now we can only see my face in big. Yeah. Okay. Thanks.
Is that good now?
Yes.
Cool. Sorry about that introduction. Okay, so we've got this notion that we want data that gives us lots of information gain, i.e. good collapse of our posterior entropy, and therefore we want designs that give us data that have this high information gain. Obviously, though, when we're making our design decisions, we don't actually know what data we're going to see, so we can't directly target this information gain. So what we target instead is what's called the expected information gain. And that is just to take an expectation of this information gain over the possible data. So we can talk about the expected information gain in theta is our entropy of essentially a prior over theta minus an expectation over the possible data of a posterior entropy over theta. We can also rewrite this if we want, because it's essentially it's a mutual information. So that we can also think about this as the mutual information between what we're learning about theta and these responses y. So we can equivalently, we can say that it's the entropy of the marginal predictive on y, essentially our prior predictive entropy, minus the expectation of the true theta of the entropy of the likelihood. And what's really important to appreciate about this thing is that it's now something that's just fully defined by a joint generative model. So this is where the sort of Bayesian experimental design element is really coming in, because we are essentially defining a Bayesian model by defining this kind of joint distribution over theta and y. And once we've defined that, that fully defines this expected information gain, and therefore we can then start using it to go and actually make these design decisions and gather data. So that joint model, it can kind of take any form. So sort of traditionally, it would take the form of a kind of conventional Bayesian generative model. But it can also be a machine learning model, or it could be some big stochastic simulator. And as we're basically going to use in this talk, it's going to be actually something, it's not going to be the LLM itself, but it's going to be something that's derived from that LLM in a kind of algorithmic way. And just to sort of drive this point home a bit more, once we've got that joint model, it's defining all of these other terms for us. It's going to define our prior belief distribution. It's going to give us this sort of marginal predictive distribution over possible data. And it also gives us a way of deriving these kind of posterior beliefs after we see that data. When we come back, though, and we think about this model in the context of that expected information gain, it's important to think about the fact that it's actually sort of implicitly using the model twice in the definition. So we are using the model both here to sort of define the notion of the information gain, and we're using the model to kind of take an expectation over that. So we're sort of using the prior predictive to simulate possible data, and then we're trying to sort of maximize under an expectation, and that's that simulated data, the information gain in our model. Where this approach really starts to get particularly powerful now is when we start thinking about using it sequentially. So the sort of coherence of Bayesian methods means that we can essentially think about taking our model, and then once we update our model with some new data, we're going to get an updated model, and therefore this is going to define a new expected information gain. So we can do what's known as sequential Bayesian experimental design or Bayesian adaptive design by kind of iterating between maximizing this expected information gain to choose a design, or in our setting, this query. Then we're going to be able to sort of run the next step of our experiment. So here we're going to actually pose that query and get a response from the user or the external environment. And then we have to have some mechanism to sort of update that model in the background. So traditionally, this would be a Bayesian update of our model to get an updated sort of posterior that then becomes our prior, that then allows us to update things. And we're going to be following the same framework, but we're going to kind of maybe break some elements of these slightly. So we're not going to be doing full posterior updates, but we're still going to be going through this cycle of having a model, using that model to choose the best query, running iteration of the experiments, and then updating our model. And just to sort of write this a bit more mathematically, if we have our updated model here as this now joint over theta and the next response yt plus 1, that's a function of our current query xt plus 1 and our history ht. And this updated model is just going to define an EIG, an expected information gain, in the same way as we had before. So before we had the difference in prior entropy to expectation over posterior entropy, and it's the same thing here. We have the entropy of p theta given ht, noting this is independent of our query itself, minus the expectation over this possible data now given the history and the next query of the posterior that we'll get, posterior entropy we'll get once we've seen everything. So we've got this mechanism where we can just iterate between updating our model and then using this expected information gain to go and choose these designs. So this is probably just a good point to quickly pause if anyone's got any questions before I go into the BED-LLM approach itself. Okay, if not, I'll just keep going. Do feel free to interrupt me if anything's unclear. So at this point, we've got this idea that we have the notion of sequential Bayesian experimental design, which gives us this sort of information theoretic way of making these design decisions in a sequence. And we've got this idea that we want to sort of make these iterative queries with a large language model. So at a very, very high level, this BED-LLM approach is just going to be a combination of these two things, where that model comes from the LLM and we make decisions using Bayesian experimental design. But we'll see in what comes, there's actually quite a few nuances in how we're actually going to do that. Before we sort of go into those, though, let's just sort of carefully go through exactly how this is going to work. So each step of the BED-LLM process is going to go through 4 key steps. So the first thing we want to do is we want to generate some set of candidate queries. So we're not going to be able to use, say, gradient methods or anything like that to optimize queries here, because sort of optimizing in the space of that LLM is just really not going to be viable. So we're going to use the LLM to itself propose possible questions. But rather than sort of naively having it to propose one question and just using it, we might get it to, say, propose 50 questions. And then we're going to be using this BD approach to choose between the sort of different 50 questions it can propose. The second step is that once we've got the set of candidate queries, we're just going to estimate our expected information gain for each of them. So as we've just laid out, we've got some notion, the expected information gain for each possible query. We can estimate that, as I'll explain in what follows. And then we're just simply going to choose whichever of them has the largest possible estimate. And then we just need to sort of run that and update our model to return to step one. So to sort of see how this is going to look in practice, we can go back to that 20 questions problem. So we're going to start a couple of steps in, just as a bit of information to work with. And imagine that the two questions we've asked are, was this person born in the 20th century? In this case, the answer was yes. We've also asked, is this person male? And the answer is yes. So to sort of run this BED-LLM approach, there's sort of two things we can do first. But the easiest one to think about is that we can first sort of sample some ground truths. So this theta, remember, is what we're trying to learn about. And in the 20 questions problem, that theta is the ground truth person. So we now want to sample possible people that are consistent with that history. And I'll explain in careful detail as we go forward how that's done. But for now, just assume we're basically using the large language model to generate these samples. So here, some people that are male from the 20th century would be things like Barack Obama, Steve Irwin, Frederick X, Banksy, Elvis Presley, and so forth. The other thing we then need to do is generate these candidate questions. We need to say, what questions might we ask next? So we're just going to here prompt the LLM to suggest sensible questions to ask next. And here are some possible examples, most of which are not very sensible. So one question would be, was this person born in Antarctica? And obviously we know this isn't really going to be a bad question, because I believe 11 people in history were born in Antarctica, so we're pretty certain the answer is no. Another bad question, though, would be, was this person born in the 19th century? And this is specifically bad because of the information we already have. We know the person was born in the 20th century, so it's a bad question. We might have the question, is the person European? This is potentially much more sensible. We have, is this person an artist? This is not a truly terrible question, but it isn't a very good one, because it's still quite unlikely that the person is an artist. So for this kind of 20 questions problem, we can think of the best question as basically the one that splits the possible hypotheses in half. So the entropy for this kind of binary thing is maximized when true and false are sort of equally likely. And so what we want is a question where the true answer and the false answer are equally likely, but we perfectly know the answer if we get it. So if I knew theta, I want to be able to perfectly predict the answer. And I also want basically complete uncertainty in my ability to predict it if I don't know theta. So here, if the person's an artist, it's much more likely they're not an artist than they are an artist. And so this isn't going to be as good a question. The final question we could consider is, does this person prefer thrash metal or death metal? And again, this is really not a very good question, but it's a bit more subtle now why it's such a bad question. So here our predictive uncertainty is basically maximum. We probably know almost nothing here. It's pretty equally likely that we'll get false or true as our answer. But we're not going to learn anything really once we know it. So that answer is really not going to actually help us. And this is why we work with this expected information gain rather than just the predictive uncertainty, because we need the notion of, are we actually learning anything if we actually get the answer? So, for example, here, if I know that the person is, say, Steve Irwin, it's unlikely that the LLM even knows if Steve Irwin prefers thrash metal or death metal. So even when I know the true theta, I'd still be uncertain here. And therefore, we can kind of see that it's still going to be a bad question. So going back to sort of algorithmically how we're going to do things, we're going to estimate those EIGs. And as you can see here, we'll get very sort of low EIGs for these bad questions. So the person who's born in Antarctica will probably get some tiny value. We could argue we get exactly 0 if they're born in the 19th century, because we know they're not. If the person's European, gives us a good score of, in this case, 0.8. The person's an artist, a bit lower. And the question, do they prefer thrash metal or death metal? It's probably not going to be totally zero, because it could be that the person was, say, a metal music artist, where you might have had some notion of the answer. But in general, this is not going to be something that's very useful. In this case, then the best question for us to go with is, of course, is the person European? That's definitely the best of those five. And we might get the answer, in this case, no. And then when we move on to the next step, we basically have to just update these beliefs at theta. So the simplest thing we could do is we could say, well, we've got this sort of set of samples, and I could just eliminate now all the ones that are not compatible with the new response. So this is kind of essentially would now be a Bayesian update under a likelihood model that's a sort of a 0-1 likelihood model. And I can just kind of start thinking about eliminating all of these people. And then I've got a new sort of set of samples from theta, and I can kind of continue with the next step and keep going. However, there's some pretty big things that I've kind of glossed over in this process. And probably the biggest of those is, what is the actual model that we should be using in this formulation? So I've said we're going to do the EIG. I've never really said how we're going to derive that EIG. I've just sort of alluded to the fact that we're going to use the large language model. So we really need a concrete way to set up a proper Bayesian model, a proper joint model here, that we can then utilize to actually formulate the EIG. And we also, in particular, we really need to know how we're going to update that model. So it may not be really viable for a lot of problems to say, go and do a full Bayesian inference here. The kind of the traditional setup of just estimating some posterior, it's not likely to work at this kind of huge LLM scale that we're working with. So let's think now first about this former problem of how should we be setting this model up if we want to go and estimate this EIG. And the thing to realize is that actually that there's a really important kind of high level design decision that you're going to have to make here. Because there's actually multiple different ways that you might derive a joint model from that large language model. It gives us a way of basically generating lots of distributions. And in particular, there's two ways we could kind of set it up. So the first way, and in some ways the most obvious way, is we set things up like a normal Bayesian model. We utilize the LLM to construct some kind of prior, and we utilize the LLM to construct some kind of likelihood. We plot the two together, and that gives us a sort of normal joint model. But there's actually an alternative, and the alternative is what I'll call a data estimation pairing. And with the data estimation pairing, what we're instead going to do is we're actually going to derive directly a distribution over possible new data. And then we're going to derive some kind of estimation distribution over theta given that new data as well. So this is kind of a bit like the sort of martingale posterior thing that Fong and Holmes came up with, in the sense that we can think about sort of simulating data, and then once we've simulated data, estimate from that new data. And what's unusual about the LLM is that we have the flexibility to kind of do things both ways, because we can just sort of ask the LLM to essentially give us a posterior. If we give it some new data, we can just say, well, what's your updated distribution given this new data? Again, we can get it to marginally simulate new data we might see. So in some ways, both of these sort of formulations are kind of equally valid in this LLM setting. There might be some complications, as I'll come to in a sec, but they're going to give us two pretty big different forms that we can work with. Moreover, they're going to really not actually give us the same behavior. So LLMs are not proper Bayesian models. So I'm not going to get the same distribution, even if I just sort of sample theta and then sample the response, than if I sample the response and then I sample this theta. I also might want to change some of these terms. It may be that I want to use the large language model, say, for my likelihood, but not my prior, or I might want to use it for, say, my marginal data distribution, but not my posterior. So there's actually quite a lot of sort of options here, and we need to sort of think about actually what's going to be the best way to set this model up. So for our work, and when we're using BED-LLM, we're basically going to mostly work with this prior likelihood pairing. And there's going to be some important reasons for this. So the first of these reasons is a sort of a more practical one, which is that when we work with these marginal distributions, either the prior or the marginal data distribution, then it should be relatively easy for us to sort of deviate from the LLM's internal beliefs on this. So we can, in particular, we can kind of think about having some sort of algorithmic sampling procedure for each of these, where maybe we generate some samples and then reject them, or we actually have just some sort of process of like a chain of thought inside the LLM, or the LLM generates things and then rejects them itself. There's lots of sort of engineering algorithmic things we can do here to make these kind of sampling distributions on those marginal distributions. But when it comes to those conditional distributions, we're not going to have the same flexibility, because for those conditional distributions, we actually need to evaluate the entropies. And that means that we're going to really utilize the sort of the full distribution when it comes to these conditional forms. So if we kind of skip back a bit through the talk, and we sort of look at these two forms of the expected information gain. So we've got this notion that we kind of look at it as prior entropy minus expected posterior entropy. So in that form, while the prior entropy doesn't depend on the designs, we can ignore it. Then we've got an expectation over data of our posterior entropy. So we're just sampling from this marginal distribution of data, but we're calculating the entropy of this posterior distribution of theta given the data. And then in the bottom form, we have things sort of flipped. Now we've got the entropy of the marginal, which can be itself formulated as the expectation of the likelihood, minus the expectation over possible theta, the prior, of the entropy of the likelihood. So in the second form, we can't get away from actually having probabilities and entropies of our likelihood, but we can just sample from the prior. And then on the top form, we can just sample from the data. We actually need to evaluate probabilities and entropies of the posterior. And this is then what's basically going to dictate which of these forms we should actually go and use, because we're going to essentially be able to sort of trust our LLM much more on one of these than the other. So when we have these conditional distributions, we're going to need to sort of trust the LLM's ability to actually have probabilities there, so that we have meaningful entropies, so that we can instead get a good EIG. So to give kind of a simple example of this, imagine I'm kind of generating code, and so theta is the kind of correct code that is being generated. Then if I work with my data estimation pairing, I'm going to rely on the LLM actually being able to calculate entropies over the space of full bits of code. And usually the LLM is going to give me complete nonsense on that. I'm not going to get a meaningful entropy out of the LLMs in context distribution over possible code. But it might be that the outputs of the code are very simple. It may be the output of the code is just a binary variable. And so my ability to have the LLM evaluate the entropy over these binary responses is going to be a much simpler thing. And therefore, I can potentially rely on the LLM's in context distribution for that instead. So what this kind of ends up boiling down to is that if the responses to my questions are simple, then I should try and use this prior likelihood form, because the LLM can model a good effective distribution over the possible responses, and it can have good uncertainty estimates in those responses. On the flip side, if I have a simple sort of theta, a simple target I'm learning about, this data estimation thing is going to be much more effective, because I can actually use the LLM to get reasonable, meaningful uncertainties over that theta, but probably not over the responses. So an example for when you want to use this data estimation approach would be if you're kind of doing automated scientific experiments. So it might be that, say, theta is whether you're a binary thing of if a hypothesis is true or false. But then we might be generating very complex data to try and evaluate this. And in that scenario, it's really important to sort of work with something that only estimates entropy over this binary variable. Whereas if we're doing something like this 20 questions, we want something that will evaluate entropy over these binary responses. And so we want to keep that entropy in the simplest possible space. So when we work with Bedlam, we're mostly going to look at this prior likelihood setup. So we think that most problems that are going to be of interest are going to be ones where we have a simpler response model, but potentially quite a complex underlying thing that we're learning about. And so we're going to work with this prior likelihood. And moreover, we're going to use the LLMs in context distribution for that likelihood. So that likelihood is also the thing that is kind of nested inside that expected information gain. So it's something we are calculating again and again and again. It has to be cheap. We need its exact probabilities. So it's hard to sort of vary algorithmically from just the LLM's distribution for computational reasons. And we're just going to use it directly here. But for the prior, we're actually going to deviate. We're going to see in a sec that the prior induced by the LLM, given the history, is actually very ineffective. And we're going to do a more almost Bayesian approach actually to derive that prior so that we can work with things effectively. So specifically, we're going to use a sort of a combination of in-context learning and then a more rejection sampling based approach to kind of derive what this PF is, where PF is essentially that beliefs that we've got about what we're learning about these theta variables as we go forward. It's probably another good point, though, just to sort of briefly pause for questions if anyone has anything they wanted to ask. Okay, if not, I'll just keep going. So we've at this point we've got the sort of this form of the joint. So remember, the joint fully define the expected information gain. Once we've got that joint, it's just sort of turning a computational crank to go and choose our queries from it. And we've got that joint is being based on the LLM's kind of predictive distribution on answers given these ground truth theta and a particular query, coupled with this sort of PF, which is our belief state, or what I'm going to call the sort of filtering distribution on our current beliefs about what we're learning about. So to sort of see with that distribution, that sort of prior essentially we're using, why should we not just use the LM's belief distribution for that? There's sort of two kind of key reasons for this. So the first is that for this kind of problem, in context learning is actually much, much worse than you probably expect it is. So we know when we use LLMs that we can have these sometimes quite long conversations with them. We can give them lots of examples, and they can do often quite remarkable kind of tailoring of what they're doing to what we've told them. But usually when you're doing that, everything you're doing is sort of pointing towards the same goal. Each bit of thing you're giving them is extra clarification, it's extra sort of complementary kind of information that is helping sort of define a problem for it and helping it find something it's seen before. But if we take something like this sort of 20 questions problem, there's something a bit different going on. So firstly, no matter how much data that LLM was trained with originally, it can't know the answer to this question. You're not actually getting it to answer something that it's find out from the internet. It's something specific to you. It's the user's information, so it can't know what it's kind of targeting. And it turns out this makes the problem a lot harder because of how they work is really this retrieval of kind of the sum of information on the internet. And the second thing that is going on is that kind of each of the responses you're giving it is much more kind of distinct in the information here. So if I tell it that someone is an artist and I tell it that someone was born in the 19th century, and if I tell it that they were male, these are sort of all completely kind of independent pieces of information that it's having to kind of stitch together. And by the time you say have 12 or 13 questions here, all of which should be really independent because that's good design and you want them to be independent to do the design problem well, the harder and harder it's getting it for it to be able to stitch this all together to something cohesive. And that's why these kind of catastrophic failures start occurring, as shown from the example at the start, because it really struggles with all the sort of distinctive bits of information you're kind of throwing at it. So basically, when you actually try and use the PLLM's distribution on these theta, what's immediately happening is essentially that it's not properly accounting for the history. It's not taking on all the information it should have from that history, and it's not producing usually sensible distributions. The other thing that goes wrong that people may have seen when they've used LLMs is that they tend to be very overly aggressive and overconfident. They will tend to collapse to a small number of possibilities far too quickly. So to give an example of this, if we say, is this person known for their contribution to science? No. And are they known for their contribution to the arts? Yes. Then almost half of the time it will think that this person is Vincent van Gogh. And most of the rest of the time it thinks it's either Frida Kahlo or Salvador Dali. And there's no information here that's been given to it to really indicate that it should have collapsed its beliefs so much. But it's just sort of the way that they've been kind of trained, that they often sort of like to jump to responses. Essentially, they're sort of almost hallucinating the answer, but in a surprisingly kind of reliable way that they sort of keep going back to the same thing. So this isn't a good prior. This is not a good sort of human prior over possible responses. We don't want it to be as collapsed. So to get around these kind of issues of not taking on board the information from the history and also avoiding the sort of over collapse on certain possibilities, we're going to do a series of different things. So the first step we're going to do is we are going to take that in context distribution and we're going to generate some samples from it. But when we do that, we're going to do a lot of tricks in the background. We're going to have a high temperature. We're going to not IID sample. We're actually going to sort of ask the LLM to sort of generate 50 samples at once so that they're all just different. We're going to do lots of careful prompting work. There's going to be a lot of like engineering basically that goes on to try and really make those initial samples diverse. Then we're going to discard any duplicates. And we're doing that because we kind of don't really want to keep that prior differences. We don't want to sort of keep its preference to one possible answer over another. We're usually going to sort of try and enforce as close to kind of a uniform prior as we can over the possibilities it's able to generate. And then thirdly, and most importantly, we're going to go back through the previous data and we're just going to check each of those samples against the actual answers we've seen. And we're just going to reject any ones that are not compatible. So the effect of this is probably easiest to see again on that 20 questions problem. So if I say that the answer is Albert Einstein, then it can really reliably tell me the answer is Albert Einstein male. So when you tell it the truth, they're very good at answering these questions. It's this reliable likelihood that we can actually kind of get out of them, but we don't in general have this reliable updating on theta. So if it generates those samples, it can actually be really good at kind of essentially self-checking by going back through all of those previous answers. And then if one of them is incompatible, it's essentially using it as a kind of 0-1 likelihood and rejecting that sample from it. So this is why I sort of said it was kind of a filtering distribution, because we're kind of sampling a set of them and then we're sort of filtering through that set of samples to get some left. We're also actually going to do filtering in a kind of, in some ways, in a bit of a particle filtering sense, in the sense that we're going to keep good samples at each step, pass them on to the next one, generate some new samples, and then this is going to make the whole system somewhat more efficient. The last important bit that we sort of need to cover here is just the actual estimation process itself. So from before, we got this definition of the expected information again, EIG. As I said, it's fully defined by the joint model. And essentially, there is a sort of a Rao-Blackwellized single intractable estimator that we can use whenever y is discrete. And it's relatively straightforward. We're just going to draw these samples from P of f, and then we're going to calculate this sort of quantity shown here, where we're going to sum essentially over all the possible responses and take a Monte Carlo estimate of the entropy. The Monte Carlo estimate over the theta, I should say, of the likelihood times the log likelihood minus this sum over all the truths of what is now essentially an estimate for the marginal entropy, where we're taking the average over theta to get the marginal likelihood, and then we've got marginal likelihood times log marginal likelihood. If instead we can't enumerate over these responses, we can instead use schemes like nested Monte Carlo. There's something called the PC estimator, which is a contrastive estimator for these kind of nested expectations. So there's various ways we can do this, and they're sort of all based on existing literature. The sort of important point I'd like to make, though, here is it's very important when we do this that we don't assume that the likelihood is deterministic. So even in something like this 20 questions, it's going to turn out to be quite problematic to assume a deterministic likelihood, even if we expect that to be very close to the truth. And the reason for that is that if we take a deterministic likelihood, we're going to lose any sort of notion about expected change. If you assume that likelihood is deterministic, you'll break down to just working with marginal predictive entropy, and you'll lose a lot of the nuance that's to go with this expected information game. So to give a simple example to explain this, imagine what we're trying to do is make film recommendations. And two questions we might consider here are which ice cream flavor feels like the best match for the user, or which film genre does the user most prefer? Well, both of these are going to have pretty high predictive entropy, but the first question here is going to have a terrible EIG. It's obviously a terrible question because it just doesn't inform us at all about the thing we're learning about. So it's important to have this notion about learnability, and any assumptions we make on the likelihood here, such as a deterministic likelihood, can really undermine our ability to actually get rid of these ambiguous or irrelevant questions to the problem that we're not working with. So there have been other previous attempts to do sort of Bayesian experimental design things in this LLM setting, but they've all assumed this deterministic likelihood that's really undermined their actual ability to do things. Okay, so I'm going to skip over that because I'm running a little bit behind on time. And I'm just going to finish off by going through some of the experimental results that we've managed to get. So the baselines we're going to compare against are what I'll call naive QA. And that is basically just going to be to use the LLM directly. So we can just ask the LLM, please choose a question, given the history, like we did at the example right at the start, where we're just sort of prompting it and asking us to give us answers. The other thing we can do is we can use sort of maximum predictive entropy. So whichever, we're going to choose a question for which we're least certain about the answer for. And this is what sort of previous attempts at doing kind of more model-based decisions has been within this LLM context. So this is just going to be using this sort of direct marginal entropy estimate. We also need to think about having an answerer. So when we simulate these, unfortunately, we don't have access to a bank of real people to test them on. So we're going to test with what I'll call an answerer LLM. So this is just going to be a separate LLM that has hidden access to the truth. And it's just going to basically emulate a person as a responder. So it has no notion of the history. It doesn't use anything that the questioner does. So they're totally separate instances. And we can just think of this as kind of an emulator for an actual person giving responses. And so here are the sort of summary first of the results for 20 questions. So here we've got 3 different categories. We could do 20 questions to find animals at the left, celebrities in the middle, or things on the right. And what we see is basically very comprehensively, again and again, this BED-LLM approach is significantly outperforming both using predictive entropy and this naive QA approach. So the y-axis here is the success rate, i.e. did we actually get the thing that we're trying to search for in 20 questions? And you can see here we're sometimes going from like sort of 15, 20% in some cases success rate with just the LLM up to 80 to 90% accuracy with this BED-LLM approach. We also see here the entropy does distinctly worse than BED-LLM. So this is it's perhaps surprising sometimes how big this gap can be. So remember, with entropy, we're assuming a deterministic likelihood. And you might assume that in 20 questions, you almost always know the answer to the question if you know the person. But in reality, there's a lot of questions where the answer would be ambiguous. So you might say, is this person most known for contributions to sciences? And if the person is Leonardo da Vinci, then you might answer yes, you might answer no. You might also have the LM generate these kind of irrelevant questions like what person's favorite flavor of ice cream is. And we see that working with the proper EIG is really actually practically important to avoid these kind of bad questions that can otherwise come out. It's also, of course, important here to sort of test what happens when we use different LLMs for the question and the answerer. So these results here, we're using either Quen, Mistral, GPT as both the questioner LLM and the answerer LLM. So this is kind of a well-specified model scenario because our response model is equal to a likelihood. But we can also test the kind of model misspecified case by having a different answerer to the one that's been used in our BED-LLM setup. And we find that the gains actually get quite well maintained here. So in general, everything does a bit worse, but it's still very much the case that the BED-LLM approach does a lot better. We can also can compare to lots of other sort of approaches as well. Given I haven't got much time, I won't go through this in too much detail. But here we're also comparing to things like that data estimation setup. We're comparing to using the LLM to choose between questions itself rather than doing EIGs. We have, if we don't do the filtering over our hypotheses, and we basically find that all of these cases every time do quite significantly worse than this BED-LLM approach. So it's quite a surprisingly consistent big gain of doing things in this kind of careful, principled way. Finally, the other experiment we look at is to do film recommendations. So here, this underlying feature that we're targeting to learn about is something much more complicated because it's itself actually a full paragraph. We are trying to learn about someone's film preferences, and to do this, we set this feature up as a paragraph describing their film preferences. So this is something where we can't estimate uncertainty in that space. So the LLM cannot reliably estimate any decent uncertainty in the space we're actually trying to learn about, but we can still learn effectively in that setting. And it's this key prior likelihood setup that's going to allow us to do that. So even though we can't get good uncertainties out of possibilities on theta, we can get good uncertainties out on multiple choice questions. And therefore, we can still do this approach where we only have to look at entropies in that answer space and therefore do the whole approach. What we find here is again, the BED-LLM approach does better than this naive and these entropy-based methods. It doesn't do quite as big a jump for this problem. The baselines essentially do somewhat better than they were doing on the 20 questions, but we still see a pretty comfortable, consistent performance. And again, in this case, actually, the performance gain can get even bigger when we have these misspecified models. So here, again, is the case where we have a different question LLM and answer LLM. And interestingly, this can harm the naive method as well. So in this case, the naive method gets particularly harmed by that model misspecification, but the EIG turns out for this one to be somewhat more robust. Okay, so to wrap things up, the key takeaways have been basically that Bayesian experimental design really can work at this huge LLM scale. So we can take this sort of foundational statistical decision theory and we can apply it all the way up to this large language model scale, and it can really give us big improvements in how we can gather information and how we can kind of ask questions. However, we do need to be very careful as we go it up about exactly what the joint models we're going to use to set things up are, as well as things like the estimators and everything that we set things up with. But if we're careful and we design these in principled ways, we can get very effective approaches. Finally, and perhaps in some ways particularly importantly, we can do this in spaces that we cannot get LLM uncertainty in. So there's a lot of research that goes into how we estimate uncertainty in LLMs. And what this is showing is a lot of the time you can sidestep that. Don't need to get LLM uncertainties in big complex spaces as long as you can draw representative samples and you have another space, your response space, that you can go and actually estimate uncertainties in. With that, it just leaves me to thank you very much for listening and thank all my co-authors. Deep Pro was the lead author on that paper. He's a PhD student in my group. And then we've also had lots of help from Sinead, Alan, Michael, and Yijie at Apple. And then Ning and Freddie. Ning is my former student now in Hong Kong, and Freddie is another current student of mine. So thank you very much for listening, and look forward to taking any questions.
Okay, thanks. So give the floor.
Sorry, I didn't hear
that. You got a round of applause. Okay, I think there was a question in the chat we can start with. We've got a couple of minutes. Do you think there would be any benefits in using multiple LLMs to obtain PF, like using an additional voting mechanism?
That's a good question. Yeah, yes, I think so. I think you're going to increase the cost, but the key to that sort of PF, it's quite like doing rejection sampling. You need a good proposal that has good coverage. So you want to basically get something that will be as diverse as possible, and then you rely on rejecting those samples. So a lot of the work we do is in ensuring that diversity, and we in the final version we didn't do this, but in previous versions we were doing things like sampling extra features, then conditioning on the extra features to just force more and more diversity. When you work with LLMs, their uncertainty is really rooted in their autoregressive nature. You have to kind of simulate things out to get that diversity. So doing stuff like having multiple LLMs would be a really good way to try and kind of like force this.
Okay. I'll take one from the room, and then we'll go to you, David. Yep. Do you want to come up? Well, yeah. It's probably complicated.
Yes. Hi, Tom. Can you hear me? Yeah, good. Okay. So I was just wondering, with the naive approach, did you consider comparing them more in the sense of how many questions does it take for a success? Because the kind of naive LLM approach feels like, I mean, to do your approach, you have to call the LLM quite a few times and sort of screen the questions, if you like. So somehow for the same computational effort, you could arguably ask more questions the naive way.
Sure. So we are running things actually right now a bit around that. So we just submitted this paper a few weeks ago, and one of the things we're running to wrap things up is a bit this. I think the key point here is that you're usually willing to have more calls of the LLM in these scenarios because the bottleneck is the human time. So we're standardizing this in how many times does the human interact with the system, rather than how many things happened internally. So obviously the LLM is doing more work, but the LLM's time is sort of usually less valuable than the users. That said, certainly for this 20 questions problem, basically the LLM just gets stuck. These curves sort of don't kind of keep going up to the same level if you kind of keep running it. So if I want to say I'll set a threshold of like 70% or something, how many questions to get to 70% accuracy? Most of the time the LLM will just never get there, because as its context gets longer, it gets less and less effective with that. The answer I think is often infinity, depending on where you set it, and that there's this human time versus LLM time component.
Okay, thank you.
Okay, David, you had a question?
Yes. I think the trouble with LLMs is that the people who produce them will not admit that the information doesn't exist on the web to answer most questions. And that's why they behave so terribly uselessly in many cases. The assumption seems to be that if you search enough of the web, you're going to find the answer to any question, and that's simply not true. It's not true of many questions, in fact. My experience of them has been pretty dire. Did once answer a networking question successfully. That was quite useful. But on the whole, they've been pretty horrible. You can lead it to any answer you want, Prasad, and you say, "Oh yes, but what about so-and-so?" And it replies in this horrible mock humility that, "Oh yes, thank you for reminding me of that." Ugh. and you can lead it into any answer you want in the end, almost. If you ask, for example, about Bayesian versus frequentist.
That can certainly be true a lot of the time, and I think part of what we're sort of saying with these is how we can make it do better in cases where it doesn't know the answer and it needs to ask questions, because it's this overconfidence is a big issue, and one way of kind of overcoming that overconfidence is to get them to ask for more information when they need it. And I would say a lot of what we're looking at is here where it cannot know the answer because it's specific to a person. And how do we get it to sort of ask questions in a way that's effective for that?
Yes, thank you. The best definition I've seen is that they're good at giving things that look like an answer, but may not at all be an answer.
I know we've gone past 3. Okay to hang on a bit more, Tom? We've got some questions.
Yeah, that's fine.
Cool. FX.
Hi, Tom. So my question is like much broader, big picture, I guess. So obviously you've kind of made some references to importance sampling and various other things. And of course, I know that you've worked quite a bit on Monte Carlo methods. So in this sort of context, is there scope for using slightly more clever Monte Carlo methods, or is it that some of the kind of spaces are a bit too hard to work with to make it work reliably? So my understanding is that for the objective, you use kind of some sort of naive Monte Carlo or some sort of maybe nested Monte Carlo. Is there something you could do there, or?
I think it'd be difficult to do any formal methods. I think you could argue that some of the algorithmic things we are doing have relation also to more advanced methods themselves as well. So when we kind of do some of this diversity sampling, it's kind of like sort of variance reduction, sort of, Latin hypercube type thing that's going on, in the sense that we're like trying to force it to sort of spread out through the space. Formally doing more advanced things, I think it is not going to be viable, because it just, everything's too expensive to call. All your uncertainty estimates are pretty unreliable. Everything's kind of in some ways implicit. So I wouldn't see you guys say doing Bayesian quadrature here, or an MCMC method. I think is going to be quite hard, but I think a lot of the principles you have from those methods can really guide how to do good engineering with the LLM in how you do this.
I guess the one I was thinking about was more something like quasi Monte Carlo, because I see like a lot of what you're doing is based on generation. So you could like use some of those tools to maybe get better diversity in the generation.
I would argue that we, to some extent, are doing quasi Monte Carlo.
Yeah, that's right.
We co-sample rather than independently sample, and we tell them they all have to be different, and we put other bits and bobs in there that all move it, I would say, towards things that I think formally it probably is a quasi Monte Carlo estimator if you really want to actually analyze it, because you're very much not independently doing these samples, and like if you want to show convergence, you've got weird ergodicity stuff in those estimators that you wouldn't usually have. None of which is particularly relevant because the LLM breaks down when there's too many samples anyway. But I think it's fair to think about this as kind of quite quasi Monte Carlo-y.
Okay, thank you.
Okay, there's 2 more questions in the chat, and then we'll finish off. So it's, I was wondering what work has been done to use BED-LLM evaluations, e.g. recursive prompting, to elicit information as to capabilities, risks, and the trade-off.
So that you can do some planning ahead with these things versus doing better sort of EIG estimates. What we did some initial tests, and we basically found that most of the planning ahead here has very nominal benefits and is much less helpful than just kind of more accurately trying to actually estimate the EIG. You certainly could, if you want, make a full like Monte Carlo tree search style setup here, and kind of simulate forward, push back, and do it that way. I think, yeah, it's a kind of question of cost versus everything else. Some papers have done some of this, and they've certainly not quoted sort of results numbers that I think are close to the ones that we're getting, but there probably is some more work you could do to sort of on these kind of evaluations.
Great, thank you. Last question regarding entropy EIG estimation. Will the response length influence that as the sequence log likelihood is the sum of all tokens log likelihoods? Did you restrict the output response format?
Yeah, so there's a lot of care in how you set the model up here. So you're only looking at the entropy of the next response. You don't have to look at the entropy of the whole set. And this is also why you often don't want to bother about planning ahead, because as you start planning ahead, your sort of ability to kind of really deal with the space properly breaks down a bit. The kind of weakness that's going on here is we've got these sort of target theta and response y spaces, and you need one of them to be relatively simple. What we usually do is we do multiple choice answers, and we force the LLM to give A, B, C, D, E, or so forth as its exact token response. So then you only have to look at the entropies over the tokens A, B, C, D, E. So the question defines the possible responses in it, and then you look at the entropies over that. So we are starting to think about, like, the next work we're going to start looking at is like, how do we start to sort of relax this? How do we start to work with more complex spaces where sort of both theta and y are sort of more complex? And that's going to, I think, be quite challenging. But at the moment, yeah, the weakness is essentially that's what we have to limit.